Okay, so in this very lecture on topology specifically, we're going to speak about a fact on real line which we can generalize to any simply ordered set. We intend to show that any closed interval in the real line is compact. Okay, I guess we are already pretty much accustomed with the definition of a compact space. A compact space is a topological space, let's say, for which every open cover has a finite subcover. Open cover is simply a set of open sets, a class of open sets whose union contains the space. So that set which contains the open sets whose union contains the space has a finite subcollection which still covers the given topological space. Such a topological space we say it to be a compact space. Okay. In real line, we intend to prove that every closed interval in R is compact in order to basically have a certain class of sets in R which we already know to be compact in that sense. Our goal is to catch hold of some particular sets, subsets of R, which we know to be compact, and the first step we take towards that is by classifying the fact that every closed interval in R is compact. But what we do is we prove the statement that every closed interval in R is compact by not restricting the topological space to R, but we assume an arbitrary topological space X, which is simply ordered, has the least upper bound property, and we apply the order topology on X. Okay, so let's start with it. So what we tend to prove, I'm writing this as a theorem indeed, that let X be a simply ordered set with the least upper bound property least upper bound property in the sense that if we take if we catch hold of a finite interval, let's say, then, or rather if we catch hold of a finite subset of X, then it obviously has a least upper bound in X. That is the thing of the least upper bound property, and we are pretty much accustomed with this property in R, right? We say R to be complete due to this property only. So which has the least upper bound property, then in the order topology, each closed interval is compact. Each closed interval in X is compact. Okay. Okay. So we start with the proof directly, and we go through step by step. So first thing we do is that, so let A be elements from X such that A is less than B. We consider the closed interval AB. Okay. Let A be an open cover of AB. We intend to show that A has a finite subcollection. Which still covers AB, and this statement definition is obvious, right? Because if we consider a finite subcollection from A where A is indeed open cover of AB, then obviously it will cover AB only. Okay, so we just need to find out, or rather you might say, give a conceptual construction of how such an open or such an finite subcover will exist. Okay, so let X, now the first step towards this is what we do is basically we construct out a smaller interval from AB, and we show that that can be covered by a finite number of sets. Okay, so let X be from AB such that X is different from B. So that pretty much defines that X must be less than B, right? Yeah. So since this has the least upper bound property, so we can say therefore there exists a Y in the interval AB such that X is less than Y, right? It is pretty much clear. Okay. Now, now if Y is the immediate successor of X, which is literally very clear, then this interval xy has only two elements, which implies it can be covered by at most two sets from A, right? So you just take two covers from A, one which covers the entire part from A to X, and one which covers the rest of the part from Y to B, and we are done, right? Right? Yeah. So, this is pretty much simple. Okay. Um, Now, so the other case is that if Y is not an immediate successor of X, right? So let Y be not the immediate successor of A, so of successor of X. That means there are elements in between X and Y, right? So what we do is that, so acha, one we don't write it like this indeed, because this will specify the existence of Y. What we say is that if X has no immediate successor, because if it has, then we are done with the case. So if X has no immediate successor, then let let us choose an element from the open cover, okay, which is A, such that X is in A. Now A is an open set, right? Now A is open. A is open. So that means that we have an interval xc by from the order topology, of course. So we have an interval xc inside A for some c in AB, right? Now let Y be in this interval. Then this closed interval xy is covered by A, right? Is covered by A because it is completely inside this interval. So this is completely inside this interval, and this is completely inside this open cover, right? Element of this open cover. So a single element from the open cover covers this particular closed interval, which indirectly means, rather, which directly speaks for itself that this closed interval xy has a finite subcover, which is a single element A. Got it? So if I tend to draw a graphical representation of this fact, then this might look like something like this. So we have A and B here. We choose a point X from here, and we take its immediate successor to be y, right? And there is no element in between. So we just choose the open cover of this form. Let me change the color one. So if we take it, yeah, so of this form, so this will cover it, right? Okay. For the other case, it is pretty trivial to draw the graph of it, right? For draw the graphical representation of it. That if it has no immediate successor, yeah, that is pretty much trivial to notice. Okay. Now what we do is that now, sorry, now let's see with the set of all the points y of AB such that y is greater than a, and this interval, this closed interval ay can be covered by finitely many elements of A, by finitely many elements of, got it? Yeah. Now see, if we apply, okay, let us do one thing. Till here, we frame it to be the set of statements 1. Okay, so this is the set of statements 1. Okay, so if we apply set of statements 1 to, in this case where x is equals to a, then what we have? Then there exists at least one such y such that this holds, right? Because we have just proved that a closed interval taken xy in the statements 1, it can be covered by a finitely many. Indeed, we proved that it needs at most 2 number of open sets to get covered, right? So at least one such y is there in C, right? So that implies C is non-empty, and if C is non-empty, then we can say that C has a least upper bound. So that means C has a least upper bound, say small c. Then what would that immediately imply? So that would immediately imply that A is less than C, which is less than equals to B. Okay. Now we name this set of statements to be our set of statements 2. Actually, we are moving step by step. So the first set of statements was step 1 of the proof. These set of statements are step 2 of the proof. This simplifies the proof basically. Okay. Okay. Now our intention is to show now we intend to show that the supremum C, it belongs to C only. Okay. Yeah. So suppose the contrary. Okay. Okay. First, let me say that if this happens, okay, so that what would that immediately imply? So that or rather that is this interval, closed interval AC, can be covered by finitely many elements, in A, right? Because that was the definition of capital C itself, right? Okay. So let capital A be an element from A such that C is in capital A. Okay. Now since A is open, it contains an interval. It contains an interval of the form open D closed C for some D in AB. Now all these cases appear from the definition of ordered topology. So if you don't know what ordered topology is, just go have a look in any topological book you have. Okay. So for some D in AB. Okay. Now if C does not belong to capital C, if C does not belong to capital C, then there must be a point Z in C, right? Such that Z lies in this open interval DC, right? Because we have assumed to be outside capital C, let's say. Okay. So there must be a Z in DC. Because if not, then D will be an upper bound of C which is less than C, small c, right? By the assumption of D. Because by assumption D is only less than C. So if C does not belong to capital C and we do not get an element Z in C, then that means that D will be the upper bound of the elements in C, right? Of the set C, and D is less than C. So we have an upper bound less than the supremum of C, which is not possible, right? So that means there must exist a Z. Is it clear? So if I draw the diagrammatic representation of this, so it is somewhat like this. So this is the A point. Here you have the point C. So here you have the point D, and Z is somewhere here. Okay, is it clear now? Is it clear from the pictorial representation? Yeah. Okay. So now since Z is in C, by definition of C, what we can have that AZ can be covered by finitely many elements of C, sorry, of A, of A, right? By the definition of capital C, because Z is trivially greater than A, right? Now suppose we need n elements to cover AZ. Suppose n elements from A covers AZ. Since this closed interval AC is nothing but closed interval AZ union closed interval ZC, so that means AC can be covered by n plus 1 elements, right? Can be covered by n plus 1 elements of A. So that would mean that C is in C, which is contrary to the assumption, because we had taken into consideration that C is not in capital C, right? Thus C must belong to capital C. Okay, so the capital C set holds its supremum, right? So we take this set of statements to be part 3 of the proof, and now we finally reach the last set of statements of the proof. Okay, so now we intend to show that C must be equals to B, because if C equals to B, then from part 3 we have already proved that the closed interval AC can be covered by a finitely many elements from A, right? That means it has a finite subcover. So C equal to B will imply that the closed interval AB has a finite subcover, which will indeed prove that the closed interval AB is a compact space, rather a compact subspace of X, let's say, because we have already assumed that it does have a open subcover, which is denoted by A, right? Yeah. So let C be less than B. Okay. Now applying, since C is greater than A, of course, so applying the set of statements 1 to the case X equals to C, we have that there exists a point y greater than c such that cy, so this y obviously is in AB. So I missed the statement, I'm not writing it again. So y is obviously in closed interval AB. Right? Cy can be covered by by finitely finitely many elements of A, right? Now, so okay, for before we give the diagrammatic representation of it, okay. So the representation is somewhat of this form that, so this is B, this is A, this is the point C, and this is the point Y. Clear? So, so now, what is the interval? Okay, so we have just proved that there exists a y such that Cy can be covered by finitely many elements of A, right? Okay, now in step 3, now AC from 3 can also be covered by finitely many elements from A, right? Now what is the closed interval? Now, or rather we say thus, the closed interval AB, which is simply the union of AC and CB, and each of them can be covered by finitely many elements from A. So AB can also be covered by finitely many elements from, can be covered by finitely many elements from A, right? Right. So that would mean, so we have here Cy. Okay, wait. This here we are not talking about B. Okay, sorry. So this is, yeah, we had chosen it to be Y. So this is AY and this is CY. Correct. Yeah. So this is the part Y. Yeah, correct. So elements from A, right? So that would mean that Y is in C. That would mean that Y is in C by the definition of C. But that contradicts, the fact that C is the supremum of C, right? Which would imply that C must be equal to B by contradiction, obviously, which completes the proof. Okay. So now the main intention of the proof, which is now coming out as a simple corollary to it, is that every closed interval in R is compact, because R is a simply ordered set which has the least upper bound property. So in the ordered topology, every closed interval is compact. We do not mention the in the ordered topology because we by default choose that to be the required topology. So that is all with this lecture, guys. In the next lecture, I will try to bring out some more important proofs in some advanced mathematical topics. So meet you guys in the next lecture.